Hello, I'm delighted for the opportunity to talk to you and give this tutorial on quantitative coding and complexity theory of continuous data of compact metric spaces. So this is a joint work with Donghyun Lim, who wrote his master thesis about this topic. And it's based on many seminal discussions, for example, with Akitoshi Kawamura, with Matthias Schröder, with Svetlana Selivanova, with Florian Steinberg, and many more. Let's start with some motivation, and the motivation is based on, starts with a discrete case. Namely, in the discrete case, we have encoding, for example, as graphs, and there's several choices of how to encode graphs, for example, using adjacency matrix or using a list of edges as these pairs of vertices, or using a rotation maps. But all these different encodings are really basically equivalent in the sense that one can convert back and forth between them, reduce one to the other within polynomial time. So as long as we're only interested in the polynomial time complexity, these are all equivalent. Only when we want to look more closely, such as maybe linear time, then there may arise some differences. On a larger scale, encoding integers usually proceeds in binary, but if one were to encode integers in unary, that is still computably equivalent, but not complexity theoretically. The difference can be as large as an exponential. So here we really want to use the binary encoding, otherwise things get distorted complexity theoretically. This is about the discrete coding theory. How about the continuous case? In the continuous case, there comes this additional requirement or condition that any computable function must necessarily be continuous, which is well known, for example, for functions on Cantor space or functions from real numbers to real numbers. And there's a quantitative strengthening to that condition, for example, found in Kerry Koh's book, namely if a function is computable in polynomial time, then it must have a polynomial modulus of continuity. So the folklore statement qualitative has a quantitative strengthening, namely in the polynomial sense. How about other spaces? There is extensive literature and investigation on how to encode other spaces for computability purposes, not really for complexity purposes. And for example, the question of how to even define complexity on spaces such as Sobolev space or the Hilbert space of square integrable function, there's not even an established definition for that. And that's the starting point of the work I'm talking about today. Our goal is for definitions and justifying these definitions in order to study complexity, polynomial time complexity, and finer graded such as linear time complexity. And to illustrate how subtle matters are, consider the purportedly arguably simplest case, named the real unit interval. What Alan Turing first considered in his paper on computable numbers was the kind of binary expansion. This seems like so natural, a binary expansion over the Cantor space of infinite binary sequences. And I'd like to point out that most of the real numbers have a unique binary expansion. Only the dyadic real rational numbers have two of them, one ending in zeros and one ending in ones, but still it's almost unique. Another encoding of real numbers that Alan Turing then resorted in a correction that he published after having realized that the binary expansion is not suitable is the rational expansion, and that turned out was then used later by Andrei Gregorczyk when he defined and discussed computability of real functions with real arguments encoded in this sense and real values returned in this sense, namely the sense of the sequence of fractions, integer numerators and denominators that approximate the real number up to error 2 to the minus n, where the numerators and denominators are in turn natural numbers encoded or in binary, and thus result in a sequence of finite binary sequences that is again an element of Cantor space of infinite binary sequences. Maybe more, and observe that in this encoding, every real number has now suddenly uncountably many such codes, such sequences. The same holds when we oppose some restriction, namely when we restrict the denominators in the rational approximation to be 2 to the n corresponding to the error bound 2 to the minus n, and thus we only encode the numerators still in binary, and thus arrive at encoding again over a Cantor space of infinite binary sequences. And the fourth encoding I want to report on is a signed binary encoding, which is basically the same as a binary, except that now we also allow for this signed -1 digits. And again, observe that now suddenly every real number has uncountably many such codes. Codes over Cantor space when we agree that the 3 digits -1, 0, and 1 get individually encoded as 2 binary digits like 0, 0, 0, 1, and 1, 0, 1, 1 being prohibited. So these are 4 ways of encoding real numbers on the real unit interval over the Cantor space of infinite binary sequences. But maybe surprisingly, the most natural or naive one turns out to be computationally completely useless, whereas the more and more sophisticated or unusual one turn out to have better and better computational properties. So the first one, namely the binary, was already observed by Turing to make addition uncomputable, and I'm not going to repeat Turing's proof. It's a simple discontinuity argument with basically due to unbounded carries. The rational encoding does make addition in all arithmetic operations computable, and is actually equivalent to the standard encoding used in real computability theory in computable analysis. But it doesn't make addition computable in bounded time. So for complexity investigation, it's still completely useless, basically because the denominators can be unnecessarily large, much, much larger than necessary in order to arrive at this, to get this error bound of 2 to the minus n. Whereas the dyadic representation kind of prevents those unnecessarily large denominators, which a Turing machine would need to read entirely in order to even access this approximation to the 2 to the minus n. So the dyadic representation implies also bound on the binary length of the numerators, and thus a bound on how many bits the computation must process and also skip in order to arrive at this 2 to the minus n approximation, namely quadratic number of bits, right? So 1 bit for A1, 2 bits for A2, and so on, up to n bits for an, and altogether this makes 1 plus 2 plus 3 plus n quadratic number of bits in order to read and to skip over most of them in order to arrive at the approximation. So for complexity purposes, this is really good. For polynomial time complexity, up to like quadratic time, but when we were interested in more closer complexity investigations up to linear time, then the scientific expansion is the encoding of choice, because there addition becomes linear time computable, and in fact computable by a deterministic transducer with a constant look ahead. And so this may be kind of surprising, but it's I'm reporting on it in order to motivate and to demonstrate that we want to proceed to other spaces, such as the Hilbert space of square integrable function, or Sobolev space, or generic compact metric spaces. The question is wide open. What is a suitable way of encoding these spaces, not just for computability, but for polynomial time, and hopefully even for linear time complexity investigation. So this is a motivation, and we're now going to report on the existing computability theory and qualitative coding theory of such spaces, due to mostly Kreitz and Weyrauch, who started studying encodings over the Cantor space of infinite binary sequences, because on this space Turing machines already can operate naturally, and thus, the goal is to encode other more general spaces over the Cantor space of infinite binary sequences. But I also must emphasize that other people like Stephen Cook and Akitoshi Kawamura, for example, consider encodings over other spaces, such as the oracle space, of a space of oracles, that is, of 0-1 valued predicates on finite binary strings, which in the sequel I'm going to call bare space, although bare space is usually meaning something different, and in particular something non-compact, whereas this space is compact. And the formalization due to Kreitz and Weyrauch from 35 years ago is to define that encoding, formalize an encoding as a representation that is a partial surjective mapping from Cantor space onto the space under consideration. And computing on such spaces, computing a function between such spaces equipped with such encoding, such representations, means to compute transformation, something that transforms names for arguments in the first space X to names of values in the second space Y. That means here this capital F is such a transformation from Cantor space to Cantor space that satisfies this condition, which is visualized or amounts to this diagram to become commutative. Here we have the encoding from Cantor space U onto the space X, and from Cantor space U onto the space Y, and the function F, and the transformation of codes must make this diagram commutative, and computing, thus computing small f, is defined to compute such a transformation. Yes, and as I said, others have considered such encodings over more general spaces, and I will return to that and generalize that, argue why it should be generalized to actually to compact ultrametric spaces, observing that both Cantor space and this oracle space, Cantor's bare space, are instances of compact ultrametric space, where ultrametric means this strengthened not triangle inequality, not the sum, but the maximum of the two. And this is a kind of extension of the research of Andre Bauer and Lawrence Berkedal and Dana Scott from 2004, who suggested equilogical spaces to be the right class of ground spaces for computability investigations and encodings. So this is a Kreitz-Weyrauch theory of representation, and what Kreitz-Weyrauch in 85 on top of this definition device our condition is a condition for what is a computability theoretically suitable, reasonable encoding representation, namely one that is admissible. So what does that mean? Let's discuss that at our first examples, the binary encoding, the rational encoding, the dyadic encoding, and the scientific encoding, now put into this framework as partial surjective mappings from Cantor space onto the real unit interval. And let's call them beta for binary, rho for rational, delta for dyadic, and sigma for signed. And let's discuss in a more abstract setting why the binary encoding is not suitable. It is not suitable because it violates a condition identified by Kreitz-Weihrauch as a requirement for computability theoretically reasonable encoding representation, namely the condition that it must be admissible. Admissible as defined by Kreitz and Weihrauch means two things. First, it must be continuous as a partial mapping from Cantor space onto the space under consideration. And secondly, it must be maximal among all these continuous representation, maximal in the sense that any other continuous representation admits a continuous transformation and continuous reduction to this current representation, where continuous reduction, continuous transformation means the following, that there exists a transformation mapping from Cantor space to Cantor space, which translates zeta names into psi names, makes this restriction. So this is the definition, and I'd like to emphasize that this categorically, this is kind of similar to NP completeness. So NP complete means in NP, which means corresponds here categorically to being continuous, and to be maximal among all problems in NP. Maybe any other problem in NP has a polynomial time reduction to that problem, and here any other continuous representation has a continuous reduction to this one. So it's maximal, means being maximal under a certain partial order, and indeed this notion of reduction is a partial order. In particular, it is transitive, partial pre-order. It's not reflexive. It's not antisymmetric. Right? Okay, so this is the definition of Kreitz and Weihrauch, and this definition is justified by the following so-called main theorem of Kreitz-Weihrauch, namely, whenever we have representations on spaces for spaces x and y that are admissible in this sense, then continuous function between spaces x and y corresponds to continuous realizes, continuous transformations of names of arguments to names of values. So we have this correspondence, and this correspondence is very important because, as you recall, any computable function must be continuous, and now it doesn't really matter whether we talk about continuity on the basic space of Cantor space or continuity on the spaces x and y that the original function is living on. Another important contribution of the Weihrauch paper is that indeed many spaces admit such admissible representation, namely sufficient is that it is a second countable T0 space. And Matthias Schröder has considerably generalized and extended that condition. It's only sufficient, not at all necessary, but this goes beyond the purpose of the present talk, so I'd like to refer you to Matthias Schröder's work on this matter. So to summarize, there's this very good theory about qualitative condition for qualitative computability investigations. Representation must be qualitatively admissible, namely qualitatively continuous and maximal with respect to continuous reduction among all other continuous representation. And the binary representation can now be understood as violating the second condition. It satisfies the first, but the second condition is violated, and this explains why the binary representation does not make the continuous function of real addition. It's a continuous function, but this continuous real function does not have a continuous realizer with respect to binary representation, and thus the binary representation is unsuitable, where the other three are suitable, are admissible quantitatively. But recall that for complexity theory, there's considerable differences between the three. So we want to find a general criterion that explains why and how these three differ qualitatively. And to this end, we're going to refine the qualitative condition of admissibility to two quantitative versions of polynomial admissibility and linear admissibility, and it will then turn out that the rational representation is not quantitatively admissible, the dyadic representation is polynomially admissible, and the sign digit representation is linearly admissible. So that's an outline of the rest of this tutorial. So all these three are qualitatively admissible and will construct and justify definitions of polynomial admissibility and linear admissibility that make the dyadic polynomially admissible and the signed representation linearly admissible. So this is the overview of the rest of the talk. We have already discussed binary, rational, dyadic, and signed representation of real numbers and the different computational properties they induce. We've discussed the qualitative existing theory of admissibility and qualitative main theorem due to Kreitz and Weyrauch. And our goal, today's talk is about we're going to refine qualitative continuity into a quantitative notion by means of columnization, namely in terms of moduli of continuity. We're going to turn the qualitative condition of compactness, or to more precisely the total boundedness, into a quantitative version, which turns out to be Kolmogorov's entropy. And then what is going to be new is our definition of polynomial and linear, that is quantitative version of admissibility, which I'm going to lead onto and justify, and the quantitative, namely polynomial linear version of the main theorem that we thus can derive and follow from our quantitative version of admissibility. And in the end, I'm going to close with some generalizations, namely from Cantor to other ultrametric spaces, as well as with some open questions that I'd like to throw out to you into the community. So let's move on to quantitative, continued from qualitative to quantitative, based on the observation that the existing definition all revolve around qualitative continuity. So our goal is to replace qualitative continuity with quantitative versions of continuity, and that will turn out to be a little bit subtle, so please stay tuned. Recall that this binary representation lacking admissibility has no continuous realizer for the continuous addition on real numbers. The rational representation has continuous but no boundedly quantitatively continuous realizer for, although addition is 1 Lipschitz on the unit interval and therefore quantitatively continuous. The dyadic representation will turn out to admit a polynomial modulus of continuity for the realizer of 1 Lipschitz addition, and the sign-digit representation will turn out to have a realizer with linear modulus of continuity for the one Lipschitz non-expansive addition. And this will follow then from our investigations and our definitions of quantitative versions of continuity that occurs everywhere in all the definitions and in the statements of the qualitative theory of Kreitz and Weierauch. Our goal is to recover and generalize, among other things, an existing characterization obtained by Kerry-Ko that I mentioned, namely that the function on the real unit interval has a polynomial modulus of continuity if and only if it has a polynomial realizer with respect to the dyadic representation having a polynomial modulus of continuity. So this is the kind of statements how we want to refine the qualitative Kreitz-Weierauch theorem quantitatively, and we want to do that not just for the real unit interval where Kerry-Ko already did it, but generically for a large class of spaces, and we want to refine that from polynomial here everywhere to linear. That's the goal. Namely with respect to the sign-digit expansion representation. So let's do that by recalling quantitative versions of qualitative continuity, namely in terms of a modulus of continuity. The way we see it, borrowing from computable analysis, a modulus here is a function from natural numbers to natural numbers that captures how close the arguments are to be in order to guarantee that the values have distance 2 to the minus n. So large modulus of continuity means it's a steep function. One needs to know the arguments very close to each other in order to make sure that the value doesn't differ too much. Put differently, this is a notion of stability, right? Stable means that changing the argument a little bit doesn't change the value much, and mu captures how much we can change the value without changing the argument too much. And this modulus corresponds to closure, right? Composition of two continuous functions. Qualitatively is continuous again. And quantitatively, if we have two functions, f and g, with moduli mu and nu, then the composition has modulus mu composed with nu, but observe that the order has switched, right? So here it's g after f, but here it's mu for f after nu for g. That's you can easily, when you prove it, you see why that's the case. But I'd like you to keep that in mind, because we're going to return to that aspect. So this is a notion of quantitative continuity, and classical notions of quantitative continuity can now be recovered and expressed in this sense. For example, Lipschitz continuity means modulus of continuity identity plus some constant. Hölder continuity means linear modulus of continuity, and they are functions that are continuous, uniformly continuous, and therefore have a modulus of continuity, but no linear, no polynomial, only an exponential one. So here's an explicit such example: the function mapping the unit interval to the unit interval x to 1 over the logarithm of e divided by x. This is a well, technically there's a singularity at 0, but it's a removable singularity by extending by saying 0 maps to 0. This is a total continuous function, but it is so steep at 0, much steeper than the Hölder continuous, and in fact it has no polynomial modulus of continuity, only an exponential modulus of continuity, because it's so steep here at 0. And when composing H with itself, which is again a mapping from this unit interval to the unit interval. Actually, the resulting function is even more steep, requiring a doubly exponential modulus, and one can keep going and thus climbing up a tower of exponentially growing moduli of continuity. So that's our notion of quantitative continuity. And let's now talk about the relation between continuity and compactness qualitatively and quantitatively. So some of the properties of the basic spaces that we consider, Hunter space and orbital space, is that their computation directly corresponds to quantitative notions of continuity, namely computing in time t means it has modulus of continuity, basically t. And we want that to carry over to the represented spaces. And to this end, we're going to consider compact domains where every continuous function is uniformly continuous and therefore has a modulus of continuity. So here's our first attempt at refining the Weierach condition of qualitative admissibility, namely the first part of the condition, namely that the representation must be qualitatively continuous. Let's say that the representation is polynomially admissible if it is polynomially continuous, namely if it has a polynomial modulus of continuity. This seems like a natural idea for arriving at a definition, but how can we check whether a given definition is a reasonable one? And here, namely, it turns out that this definition is not a reasonable one, as I'm going to explain now. That's our first tentative approach. And it's not reasonable because of a quantitative version of the statement that the continuous image of a compact set is compact again. And to this end, let's make qualitative compactness quantitative, namely using the notion of entropy introduced by Andrei Kolmogorov. Entropy is a quantitative measure of total boundedness, namely it counts the number of balls that are necessary and optimal in order to cover the space, the number of balls of given radius 2 to the minus n, with n tending to infinity. And this is kind of similar to the modulus. We always take modulus and entropy to the as exponents to the base 2. And it will become apparent why this is a great idea and natural. This has been already studied by Weierach in a paper from 2003. So this is still only reporting the existing state of the art in the existing theory. And here's some example spaces and their corresponding entropy. For example, the d-dimensional, not necessarily unit cube, has linear entropy with d, the dimension entering as a constant factor, and the size of the cube entering as an offset. Cantor space has linear entropy. Here we have a hierarchy of spaces of higher and higher type. Namely, if X is a certain space, compact metric space, then we can consider the space of all one-Lipschitz functions to the real unit interval, all non-expansive function, which is again compact space with respect to the supremum norm according to Arzela Ascoli. It's pointwise bounded by 0, 1, and it's equicontinuous, namely one Lipschitz, so it's compact again. And it has an entropy which can be bounded in terms of the entropy eta of the original space, namely the two new entropies basically exponentially larger up to some undetermined. And the actual geometric properties of the ground space, of course, matter, but they do not matter as much as this moving up from a space to the functions on this space. And I'm telling this because this construction can, of course, be iterated, considering now functions from this new space of functions, that is considering functionals with values in 0, 1, climbs up the even further, leads to entropy doubly exponential, and moving up even further the type hierarchy on arrives at again a hierarchy of towers of the entropy. And next example is the Hilbert cube with respect to the supreme norm. This is the Hilbert cube. It has quadratic entropy, something between linear spaces we have considered here and the exponential one. And the oracle space, I keep calling bare space, using terminology, has exponential entropy. We'll get back to that later. So now you have got some intuition about moduli of continuity and about entropy, moduli of continuity, quantitative versions of qualitative continuity, entropy, quantitative versions of total boundedness, scoliometrization. And the connection between both entropy and continuity and modulus of continuity is a following quantitative version of the fact that the image of a compact set under continuous function is compact again, namely if we have the function is quantitatively continuous with modulus mu, and if the domain is compact with entropy eta, then the image has entropy at most composition of eta with mu, and in particular is compact again, as we know. And this has been found and proven, for example, in Florian Steinberg's PhD thesis published in 2017. And the consequence is that any representation over Cantor space of linear entropy of the space with exponential entropy must itself have exponential modulus of continuity according to this inequality. And this means that spaces of superpolynomial entropy cannot satisfy our tentative first condition for polynomial admissibility. Namely, we cannot require polynomial modulus of continuity that would exclude all spaces of exponential entropy, in its particular all these function spaces. So that means we need to modify the definition, and we do that by allowing for a polynomial slack. We consider that the modulus of continuity can be up to polynomial in the entropy under consideration. So relative to the entropy, so if the entropy is exponential, then the modulus of continuity may now also be exponential and actually polynomially exponential. So that's the next attempt in our search for a definition of polynomial admissibility. Spoiler ahead, this is still not the end of the story, but it's already an improvement, and it leads us now first considering a quantitative version of the second condition. And the general paradigm that we're following here is how to arrive at quantitative versions of existing qualitative definitions is universally by taking necessarily inequality that is always must always be satisfied anyway, and then to arrive at a condition that we want to additionally impose. We reverse this inequality, thus impose basically an equality, but this turns out to be too strict a condition, so we're relaxing it and instead relaxing the reverse inequality. And observe that this is what we just did here, right? So the Florian's inequality said that modulus of continuity must always be greater or equal to the entropy. then we have reversed that and required that the modulus of continuity must be also less or equal to the entropy, which means they must be equal. And then we've relaxed it and said not necessarily strictly fully less or equal to the entropy, but up to a polynomial. And that's what we've done here so far. And let's do the same now also for the second condition. I call that the second condition requires maximality, namely any other continuous representation should have a continuous reduction to this current representation. And continuous reduction meant the following. And so here we also refine and turn qualitative continuous reduction into quantitative continuous reduction using the paradigm that we just introduced. So here's what comes up with this, namely the requirement that every representation now must satisfy a polynomial continuous reduction, which we define now based on the same observation that we have a necessary inequality that we've just seen here, namely the bound on the modulus of continuity of the composition. And indeed, we have here such a composition, namely the continuous reduction means that there's a translation that translates names, xi names into zeta names into xi names. And thus this condition, so that any modulus of continuity of the representation zeta must be less or equal to the composition of the moduli of f and xi. This is what you see here. Any modulus nu of a representation zeta must be less or equal to the composition of the modulus kappa of f composed with the modulus mu of xi. So this is a necessary condition according to the lowest line, and of paradigm size, turn that condition around, make it make nu also greater or equal to the composition. This is what you see here. Make nu greater or equal to the composition, and then relax that condition by allowing for polynomial slack. So this is our tentative version of polynomial admissibility, both first and second condition following the paradigm, but it turns out that this is not the right definition, because this notion of polynomial reduction violates transitivity, while the qualitative version of Keitz and Weyrauch is transitive. So this is still not the end of the story. Instead, what we suggest and introduce as definition is this way of relaxing the definition, relaxing the inequality, not with a polynomial slack, not in the value, but polynomial slack in the argument, as you can see here. And this way does satisfy transitivity. And it also tells us that we should do the same for the first condition, which you see here now with the polynomial slack, not in the value, but in the argument. And this is finally our definition of polynomial strengthening of Keitz-Weyrauch's quantitative admissibility. Both conditions, the modulus of continuity must be at most the entropy with a modular polynomial slack in the argument, and any other representation must satisfy this polynomial reduction, which also imposes an optimal modulus of continuity on the translation up to this polynomial slack in the argument. And why is this a good definition? I suppose on top of satisfying transitivity, is because now we can get and prove a qualitative version of the quantitative Keitz-Weyrauch theorem with the two statements. First, that qualitative continuity of function corresponds to qualitative continuity of realizers, and the second statement that many spaces admit a qualitatively admissible representation. So We proved in several works with Kawamura, Steinberg, Donghyun Lim over a couple of years first that this polynomial reduction is transitive. Remember, that was an important lesson that led us to change the notion of where we allow for a slack in the reversed inequality. Second, many compact metric spaces admit such a polynomial admissible representation, and I'm not going to explain in what sense many spaces. It's a technical, unfortunately unpleasant technical condition which seems hard to verify. And the next two items, C and D, are quantitative versions of the qualitative correspondence between continuity of function and continuity of realizer, maybe function having a modulus, a quantitative modulus small lambda. Then it has a realizer with a quantitative modulus capital lambda, which involves the small lambda as modulus of the original function, but it also involves the entropy of the domain and codomain, entropy of the domain here, and the inverse entropy of the codomain. Now, what does inverse entropy mean? Since entropy as a function from natural numbers to natural numbers may not be injective, it means the following, the lower semi-inverse. Also observe that our polynomial slack here comes in two places, the polynomial here and the polynomial here. So that's one direction. Quantitative continuity of a function results in quantitative continuity of a realizer. And conversely, quantitative continuity capital lambda of a realizer yields bound on the quantitative continuity small lambda of the original function, again involving the modulus of continuity of the realizer and involving the entropies of domain and codomain, but now the codomain entropy directly and the inverse entropy of the domain, and both polynomial slacks here back and forth. So that's our polynomial version of the quantitative strengthening of the Kaitz-Weyrauch qualitative theorem. And in the remaining few minutes of this talk, I'd like to discuss some strengthening, namely from polynomial to linear. So let's now replace polynomial admissibility with linear admissibility, always replacing polynomial slack with linear slack, big O, namely, so first we tighten the requirement on the modulus of continuity of being polynomial slack in the argument of the entropy to linear, and replacing polynomial reduction with linear reduction, where linear reduction now has this condition with the linear slack in the argument. And for this linear admissibility, we can prove again that this notion of reduction is transitive. The correspondence between quantitative continuity of function and quantitative continuity of realizers becomes more tighter, namely always the polynomial slack gets replaced by the linear slack, big O, Landau notation. And we have an actual example. So namely the sign digit representation that we talked about before turns out to be indeed linearly admissible, and thus we can strengthen the statement of observation of Carey-Coe that functions, real functions, have modulus of continuity polynomial slack with lambda, some modulus of continuity and polynomial slack in the argument, if and only if it has a realizer that has similar but different polynomial slacks in argument and values with respect to the polynomially admissible dyadic representation, and the strengthening using the linear admissibility of the sign digit representation says that with respect to this representation, the correspondence becomes even closer between modulus of continuity of function and modulus of continuity of realizer, but unfortunately now only restricted to the real unit interval where we have this sign-digit representation. So to summarize and conclude, there's a dictionary kind of that helps us proceed from all the established qualitative theory to the new quantitative theory, so that computability becomes complexity, topology becomes metric, continuity becomes the modulus of continuity, compactness becomes entropy, continuous image of compact set becomes Florian Steinberg's lemma, and equilogical spaces become compact ultrametric spaces, which I'm still going to explain you in the next and final slide. But let's first summarize and recap. We took the existing qualitative theory of Kreitzer and Weyrauch, based on a qualitative notion of reduction between the representation, based on qualitative admissibility of representation, to derive a qualitative main theorem about correspondence between continuous function and continuous realizer, and refined them to polynomial reduction and to linear reduction between the representation, to polynomial and linear admissibility of representations, and to polynomial and linear relations between modulus of continuity of function and modulus of continuity of realizers, based on all these definitions arrived from our paradigm of turning qualitative definitions into quantitative ones by taking a necessary inequality and flipping it or reversing it and relaxing it, but relaxing it in the argument rather than the value, because thus then we can get transitivity of the reduction relation. And finally, perspective. Yes, we've been able to show that many spaces admit polynomial admissible representation, but this condition there is very awkward to really work with, nor have we been able to show other spaces rather than the real numbers to have linearly admissible representation. So this is an open question that I would like to throw out to you into the community: which spaces do and which spaces probably do not admit a polynomial or a linear representation. Other kind of generalization is the ground space, which here used to be a Cantor space most of the time. Cantor space has this linear entropy, which prevents representations of spaces of exponential entropy, like these function spaces. Cannot have linear modulus of continuity for representations, which we took care of it by allowing relative bounds on the modulus. But it's also pretty reasonable to replace the ground space with another space that already has exponential entropy. And this is what Akitoshi Kawamura did. And thus he was able to design a representation for spaces of functions that have polynomial modulus of continuity absolutely. And more generally, since Cantor space and this bare space of ordered spaces or ultrametric spaces, one can, I'm not going to explain why, but the generalization is to consider arbitrary contact ultrametric spaces as ground spaces for representation. So that's all for me. Thank you very much for your attention, and I'm happy to answer questions.